So we're going to start this lesson by reviewing how to calculate the volume of a solid of revolution using disks or washers. So I have four curves here, y equals x squared plus 2, that's a parabola shifted 2 up, y equals 0, x equals 2, and x equals 0. And we're going to find the solid generated by revolving this bounded region around the y-axis. I'm going around the y-axis, so I'm going to put the y-axis in the middle of my graph, okay, and this is my parabola shifted 2 up, and this is the line x equals 2, and this is, again, my parabola, so this is y equals x squared plus 2. When I plug 2 in there, I see that I'm going to be at the point 2, 6. So this is my bounded region, and I want to take slices of this region and go around the y-axis. So to rotate and write an equation in terms of disks or washers, for disks, you slice perpendicular to what you're going around. So that means I'm going to slice perpendicular to the x-axis. So it turns out that I'm going to have to write two integrals because this slice is different than this slice up here. Okay? So if I think about the length of, when you're slicing horizontally, your slices are, the length of your slice is right minus left, or the big X value minus the little x value. Well, the lower slice starts at x equals 2 and ends at x equals 0. But the upper slice starts at x equals 2 and ends over here at x equals something else. It ends at y equals x squared plus 2. Let's put that in another color. So y equals x squared plus 2, but I need to know what the x value is, because remember, the length of my slice, when I'm slicing horizontally, is my big X value, or my rightmost X value, minus my smaller X value, or my leftmost X value. So I need to go back up here and figure out what is X for this equation here. So I'm going to solve for X. Let's do a little work over here. I get that x squared is y minus 2, so I get that x is plus or minus the square root of y minus 2. So it turns out I have two functions there. Those functions split the parabola into two equations. So when I'm writing this equation x in terms of y, what I'm going to get here is a positive square root, which gives me the right side of that parabola, and a negative square root, which gives me the left side of that parabola. Now, obviously, I'm dealing with the right side, so I'm going to be using the positive square root. So this is y equals x equals root y minus 2. Okay, and then I'm going to split into two integrals right here, which is where the interval changes, and that happens where the left curve switches from x is 0 to x is the parabola, and that is at the point 0, 2, or y equals 2. So for the bottom part of the integral is going from y is 0 to y is 2. Again, that is for this bottom half of the area. I'll call that region 1, which is this integral. And remember, for a washer, we are, or actually I should say properly, for a disk, the volume is the integral of pi r squared h, because that's the volume of a cylinder, a cylindrical disk. So we have pi. The radius of my disk is the x value here. And the radius here is 2 for that entire region. And then the height, remember, the height of my disk is just how thick it is, and that is the dx or the dy. Okay, and in this case, this is dy thick. Now, for the second region, which is going to go from y is 2 to y is 6, the radius is going to be right minus left. So this is actually going to be a washer because there's going to be a hole in it. And the formula for that is the integral of pi r squared minus pi r squared. I can just factor out the pi, where big R is my big radius, or the rightmost x value. Little r is the smaller radius, or the leftmost x value. So I'm going to have pi, big R squared is 2 squared, minus the little r is the square root of y minus 2 squared, which is just going to be y minus 2. I might also point out you want to make sure that you distribute your negative sign, the negative sign right here. This is going to be 4 minus y plus 2 after you square that and distribute the negative sign. Okay, that was pretty complicated because of these two separate regions, I needed two separate integrals. But there's actually another way we could do this. Disks and washers are not the only way to calculate the volumes of solids of revolution. So let's look at another method. All right, in this next method, you can see here, I've drawn the same region again. Here is x equals 2. Here x equals, oops, that's a y equals 0. Y equals 0 on the bottom. X equals 0 right here. And then this is our parabola y equals x squared plus 2, bounding that shaded region. Well, instead of slicing horizontally or perpendicular to what we're going around, again, remember that we're going around the y-axis. You could also slice vertically. And in this picture, you see I've made two slices in the shaded region. And those two slices, let's say you take that slice and you go around the y-axis, the shape that you're going to get is what's called a cylindrical shell, or just the surface of a cylinder. We call them shells. And, well, if we make infinitely many slices in our shaded region, and with each slice we go around the y-axis and get a cylindrical shell, like shells, infinitely many shells nested inside of each other, like you see here in this diagram, nesting shells, and then we add up the volumes of those shells, that's another method for calculating the volume of our solid. So how do we do that? So you can see down here in the bottom, I've got my one shell, and I'm going to unroll it. And when I unroll a cylinder, what happens is that you get a rectangle. And it doesn't look like it in this second diagram, but our rectangle has a really, really, really thin thickness to it. So let's think about this rectangle and write a formula for it. It's actually a rectangular prism. So my cylindrical shell unrolls into a rectangular prism. And we want to know what is the volume of that rectangular prism. So this edge here is obviously the height of our cylinder. And that, right here, if you look at our original diagram, that height is the height of that slice, okay? And in this particular problem, that height is a y value, or we might say f of x. Now, this edge of the cylinder, well, this edge of our rectangular prism was the circumference of the cylinder, or 2 pi r. Okay, so if we look at our diagram at the top left here, the radius in this particular picture is an x value. The radius is an x value. And again, we have 3 dimensions here. I'm going to call this third dimension the thickness or the height of the cylinder. So the volume of a prism is base times height, where big B is the area of the base times the height. In this case, the area of the base refers to the area of this rectangle, which is base times height is 2 pi rh. 2 pi r is the base length, little h is the height, and then times big H, oopsie, hold on, let's get that back there. Okay, there we go, big H. So again, this here is, this here is big B, or the area of the base, which is little b times little h, base times height. Okay, so we have that the volume of one cylindrical shell is 2 pi r h h. And we want to add all those up, and we want infinitely many of them. So in calculus, that summation of discrete units, when we have infinitely many, or take the limit as the number of shells goes to infinity, is going to give us the exact volume of our solid of revolution. And that's going to be the integral from a to b of 2 pi. In this case, our radius is x, our height is f of x, and our thickness is dx. The thickness of the slice is dx. Okay, so let's do this problem using cylindrical shells. So here we are again with the same diagram, but I've drawn a shell on the diagram, and let me talk about the things that I have labeled. So again, remembering that volume in cylindrical shells is equal to circumference times the height of the shell times thickness, okay? So our thickness, when you're trying to think about how thick is your shell, think about your slice. So if we look at the slice is this piece in the diagram that I just drew as blue there. So again, you're taking your original region, the original bounded region that you drew. So that is, here's my original bounded region. Okay? And what you're doing is you're slicing that region into little, infinitely many slices. So here I go, oopsie, that's not what I want to do. So here I go, infinitely many slices, okay? So let's say this is the slice that we're looking at in our picture right now. This is the one I have labeled H here. So if you ask how thick are all of these slices, they are all delta x thick. Delta x thick, or dx thick. And dx meaning an element of x, a tiny little bit of x. So we are taking this region from x is 0 to x is 2, and we are dividing it into really, really, really small intervals. Oopsie. Really small intervals that are the thickness of our slices, okay? All right, so we've got that our thickness is dx, and that also tells you that that is the variable you want to see in your equation. So this, again, we said our height is dx. That means that's our thickness of our slice. And then this is our volume formula. Oops. Therefore, must be in terms of x. Okay. Next, the other things that I'm looking at in my equation. So the variables that I want to be paying attention to, if you look at this equation, I have an r, an h, and a big H. And those are the variables I need to define in terms of x. Okay. So if I look at my picture, my radius is equal to x. Okay, it's equal to the x value of the point where the radius touches the curve. But and that's good because I want x's in my equation. The height of my slice is equal to the y value of the point where it touches the curve, but I can't have y in my equation. Y is the function value, or x squared plus 2. And now I am ready to write my equation. My volume in terms of cylindrical shells is the integral from x equals 0 to x equals 2 of 2 pi r, which is x, h, which is x squared plus 2, and then big H, which is my thickness, or dx. Obviously, it took some time to explain how to approach volumes using cylindrical shells, but this turns out to be a much easier integration because I only had to write one integral. Whereas when I did discs and washers, I had to write two integrals, one for the bottom half of the interval and one for the upper half of the interval. So let's do a few more of these just to get the hang of it. Determine the volume of the solid attained by rotating the region bounded by the function and the x-axis around the y-axis. This is a problem that actually has a different kind of problem. If you look at our bounded region here in the first diagram, this is the graph we're looking at, and this is the graph of this cubic function, okay? And this is the region bounded by that function and the x-axis. here, we can't slice horizontally for a different reason. If you try and slice horizontally, your slice touches the same function on the left and the right ends. So if I were saying, what is my right x value minus what is my left x value? Well, that's one problem. The other problem is it's not even possible to solve for x here. So it would not be possible to write this equation in y's. Okay, so then here's an example of we're only left one option here, okay? And that is to slice vertically and to write the equation in terms of x, okay? Which is what we're going to do. Okay, so I've got a picture here of what our solid would look like as we go, after we rotate that region around the y-axis. And then down on the bottom, I've got a picture of one cylindrical shell. So in my cylindrical shell, here's the slice. Okay, there's the slice, which goes from here to here. Again, all of your slices should be in your original bounded region. Okay, so I'm splitting that bounded region into infinitely many slices. And these slices are dx thick. All of these slices are a little bit of x thick. Okay, so again, the thickness of my slice is dx. The slice is h tall. That's the height of my slice. And this is the radius of the cylindrical shell that you see there in yellow. And again, I like to draw, sort of plot a point from the origin to where my slice touches my curve and just label x and y. So here's another problem where the radius is equal to the x value and the height of my slice is equal to the y value. And my thickness is dx, which tells me that my equation needs to be in terms of x, which means instead of y, I need to write x minus 1, x minus 3 squared. And again, the volume of a cylindrical shell is obtained from adding together the volumes of all of the cylindrical shells, the infinitely many cylindrical shells. So my volume is going to go from x is 1 to x is 3. Those are the x bounds for the shaded region, of 2 pi r, which is x, h, which is y, or x minus 1, x minus 3 squared, dx. So this one is not even possible to do in terms of disks or washers. You must use shells to find that volume of revolution, the volume of that solid of revolution. All right, in this next problem, we're going to find the volume of solid generated by revolving the bounded region around the y-axis. I actually think we are missing a little piece of information I'm going to add on here. I'm going to say the bounded region in the first quadrant, because there are actually two bounded regions. Okay, so I've sketched all three curves there. We should find some intersection points so we know how to set up our limits of integration here. All right, so I can see that my bounded region in the first quadrant is here. I need to find the intersection of the parabola and the oblique line. So let's set the y's equal to each other. I'll say x squared equals 6 minus x, or 0 equals x squared plus x minus 6. And since I'm in quadrant 1, I know that x is going to be 2. And when I put a 2 in both of those, I get that the intersection point is 2, 4. Okay, so let's draw that region on our other graph, which is there. Okay. Okay, so this is that region. Here's our point 2, 4. That oblique line has a y-intercept of 6. Okay, so when you look at a region and you're trying to decide, now you've got two methods. You've got a shell method and you've got disks or washers. I would say that instead of trying to decide which method to use, first look at the region and say, which way would it be easier to slice? Do I want to slice sideways, horizontally? If I slice horizontally, for this particular problem, I'm going to have two different slices because that slice starts at the parabola and ends at the y-axis, and this slice starts at the line, the oblique line, and ends at the y-axis. If they don't start and end at the same function, both starting at the same function and ending at the same function, then that means you have to write multiple integrals. So in this case, to slice horizontally, I would have to write two different integrals. And I don't want to do that. That's more work than I need to do. Now, if I slice vertically, top to bottom, well, then that's actually better because the top, you are always starting at the line and you are always ending at the parabola. And that is actually more ideal. One integral. Okay, so let me draw. So now I'm going to take this slice and rotate it around the y-axis, and that's going to give me a cylindrical shell that looks something like this. Okay, the slice is always the height of your shell, so this is height. Okay, and then the radius of my shell is up here. There we go. Okay, and I just like to identify a point where my slice touches the curve, at least one curve, so you can think about your x's and your y's. So there we go. From the origin, this is x, this is y to that point on the parabola. Okay, and this slice, which is dx thick, a vertical slice is dx thick. So we have that our radius is an x value. Our height, well, what is the height? The height is your top y value minus your bottom y value, or your bigger y value minus your small, oops, I wrote that in the wrong place there. Let me fix that. Again, it is your top y value minus your bottom y value, the bigger y value minus the smaller y value. And then big H is our thickness, which we said was dx. A vertical slice is always dx thick. Okay, well, the fact that our thickness is dx tells me that x is our variable in the equation. So that means that I'm going to rewrite little h in terms of x's. I can't have those y's in there. So I'm going to rewrite little h in terms of y's. So I'm going to say my height is the line where y equals 6 minus x minus the parabola where y equals x squared. Okay, and now I have defined all of my variables in terms of x, and now I am ready to write my integral. So my volume equals the integral from x is 0 to x is 2 of 2 pi, my radius is x, and my height is 6 minus x squared dx. All right, in this next problem, we are going to find the volume of the solid attained by rotating the bounded region in the first quadrant around the x-axis. So we're going this way this time, x-axis. Okay, when you're doing the shell method, you want to slice parallel to what you're going around. So a little mnemonic to help you, shell parallel. You're going to think of it as slicing parashell, shell parallel to what you're going around. So if I'm going around the x-axis, which is horizontal, my slice must be parallel to the x-axis. So that is my slice. And again, you're taking your region and you're slicing it into infinitely many small slices. So I am taking my shaded region and slicing infinitely many times this way. And how thick are all of those slices? Those, if your slice extended, it would touch the y-axis. So we say those are dy slices or dy thickness. Okay, so let me draw a shell. I'm going around the x-axis, and there is the top of my cylindrical shell, or the bottom, whichever way you want to see it. Okay, and there's the other base. And there is my cylindrical shell. Okay, so let's label some things. Remember that your height is the slice. The height of your cylinder is the length of your original slice. So this is the height of my cylinder. And then here is the radius. So remember, I like to plot a point from the origin to where my slice touches my curve. And I'm going to do that right here in the first quadrant. I'm going to label these lengths right here. This is X, and this length here is Y. Okay, this is a little bit trickier than some of the ones we've done previously. The radius is pretty obvious. The radius is the y value, and since we already said that our thickness is dy, we're okay with the radius being y because we want everything in y's. H is a little bit different here, so you have to be paying attention to quite a few things in this problem. Okay, let's move the graph down and make a little room here. I'm going to label a fixed value. This distance here, because of this vertical line on the end, x is 2, this is a fixed distance of 2. And now, in our picture, 2 is kind of split into two lengths. This length here, that's the height of our cylinder. And then this little length here, if you look all the way at the bottom of my graph there, is the x value for where a point touches your curve. So 2 is the entire length, h is the height of the cylinder, and x is this little piece down here. Again, I'm looking right down here. That's the x coordinate of a point where my slice touches the curve. So I'm going to say that the height of my cylinder equals 2, the entire length, minus the x value. 2 minus the x value. But remember, I want my equation in terms of y's. So what is y? Well, now I need to look at the equation for, so I can only have y's in my equation. So now I'm looking at the equation for the cube root function, and x equals y cubed if I isolate x there. So little h is 2 minus x, or 2 minus y cubed. So now I am ready to write my integral. The volume of my solid of revolution goes from y is 0 to y is 2. Remember, we have to be in y's. 2 pi r little h big H. Let's do one more problem, rotating a region around the x-axis. All right, so here's our next problem. We're going to find the volume of the region bounded when x equals y squared plus 2. That is the sideways parabola. If you can see down on the bottom, I have a diagram of all the curves drawn here, and then I just took the bounded region. So that is a sideways parabola shifted 2 to the right. The line y equals x, that's direct variation, linear function, slope of 1 going through the origin. Y equals 0, which is the x-axis, and y equals 1, which is this horizontal line on top. So this is another case where you certainly could use either discs and washers, or you could use shells, but it's certainly easier to slice one way versus the other. If I slice vertically, and think about your slices as being, where do I start and where do I end? I have 3 different slices, which means I would require 3 different integrals to calculate the volume. The first slice starts at y equals x and ends at the x-axis. The second slice starts at y equals 1 and ends at the x-axis. And the third slice starts at y equals 1 and ends at the sideways parabola. So that is certainly not ideal. If I slice horizontally, however, every slice starts at the same function and ends at the same function. Right to left, I'm always starting at the parabola and ending at the line y equals x. And so that's what I'm going to do. Remember, I'm slicing parashell to what I'm going around. I'm going around the x-axis. I'm slicing parallel to the x-axis. That tells me I want to do shells. Also, I'll point out that this slice is a dy slice. Again, if your slice continued, what axis would it touch? It would touch the y-axis. Or another way of thinking about it is to say, you're going to slice your shaded region horizontally into infinitely many slices that are all a little bit of y thick, dy thick. So that tells me my thickness is dy. And that tells me my variable of integration is going to be y. Okay, so let me draw a cylindrical shell rather. Okay, there's my representative for all of my shells. So I'm taking that slice that I drew and I'm going around the x-axis with it. And I am going to, let's see, I'm going to label some things in my picture. Let's label the height of my cylinder and the radius of my cylinder. There we go. And I'm also going to do one more thing. I'm going to label a point, this point here, where my curve touches the slice. So I'm going to call that XY from the origin. Okay, so let's define some things. Okay, so you can see that the radius is equal to the Y value where I touch the curve. The radius equals the Y value. And the height, remember, the height is your big X value or your right X value minus your smaller X value or your left X value. So this is on the right. Right minus left. The smaller X value is on the left. That means we're doing the X value of the parabola minus the X value of the oblique line. So our height is going to be, well, what's the X? Its X is already solved for. The parabola is Y squared plus 2, and the line X is Y. And I'm now ready to write my equation. Remember, I am adding up the volumes of rectangular prisms because our cylindrical shells unfold into rectangular prisms. Oops, that's an H, capital H. So I have that my volume is the integral from y equals 0 to y equals 1 of 2 pi. My radius is y, and my height is y squared plus 2 minus y dy. There we go. So that is our volume in cylindrical shells.